Next, let's consider page 241, theorem 9 about double integrals. Let's look at theorem 9. F of x is continuous in Rxy, and please refer to the graph in the previous page. Okay, this is Rxy as a sample. And then g, uv, and huv will be C2 functions, and such that the Jacobian is not 0 in RUV. All right, and remember that G stands for X, and then H stands for Y. So then in that, and the next assumption is that Rxy and RUV is a one-to-one relationship, okay, that is translated by G and H. And both regions are regular, simply connected, so nothing weird, nothing too weird in there. So if that is the case, then we have this double integral transformation, that is the integral of f over Rxy is equals the integral of f. We're plugging in the new variables with g and h in replacement, and times the Jacobian of the dsuv. So then this is looks somewhat similar to the original one that we know about. That is the one on the previous page, where the integral of f dx is you plug in the new variable, okay, and then you have a little thing here that's similar to the Jacobian, phi prime of t dt. So this is in 2 dimensions with double variables, and the story looks about the same. So you just stick the Jacobian here. So the Jacobian times dsuv is the same as dsxy with all other changes, appropriate changes made. And so then to prove theorem 9, let's first prove the theorem for the case when f equals to 1. So if f equals to 1, then the double integral over Rxy is just the area. All right. So then we are going to use the area formula, which is on page 225. That we have seen earlier. Let's look at it again. We'll specifically refer to page 225, this one right here, where area is the integral of over gamma of x dy. Okay, we'll use this one. So using that one, we have then area is written right here. Area is the integral of gamma x, and this one over here, okay, x dy. And then we're going to plug in this equation right here. So then now qxy is just x, okay? Plugging it in, so then this chunk here becomes just guv, because q is now just x, okay? So we'll put x in here, which is guv, times whatever the rest of this stuff here, okay? So put all that in. I think the author missed the bracket at the end here. And so otherwise it's the same thing. So we got to this line. And the integration is done counterclockwise, as we've always done. So then, and then we are going to apply Green's theorem to the right-hand side. So I have it written down here in a bit more detail. Okay, that is, we are going to this thing then equals to that, which we already have. Okay, that would be equal to write it in shorthand, will be equal to gh1 du plus gh2 dv. Okay, and then with that, we'll identify these two things, the gh1 as p and gh2 as q in Green's theorem, which is on page 224. Let's look at it again. Page 224, Green's theorem. I am not getting it. Okay, got it. Here's Green's theorem. Let's refresh our memory. Green's theorem says if we have a p dx plus q dy integrated over the line gamma, that's the same as q1 minus p2 integrated over the area. So remember that. So Green's theorem is q1 minus p2. So then so this is q1, okay, I calculated q1, which is partial derivative of q with respect to, what was q again? Q is GH2, which is G times H2. Anyway, so Q1 is with respect to U, right? Which by applying product rule, we get this thing. And similarly, P2 is this thing right here, okay, ds. Now, and then once you got the product rule out, then you notice that this one underlined green is the same as this one. So those two things cancel out, and we only have these two parts left, which is here, and that is the Jacobian, okay, because the Jacobian is defined this way, which is also written like this. And so as a result, the integral now equals RUV Jacobian DUV, and that is what we're driving for. So going back to the book, we have gotten to this part, okay? That the book is then basically the same thing I did, and eventually we got to the JUV, where JUV is the Jacobian. Now the thing is, there's a plus and minus sign here. That's because of the line integral. It depends on which way you integrate, right? It might be plus or minus or something. So then the equation has to be, it could be positive, could be negative. We have to just pick the one that is positive. So then, now we notice that there is a requirement, hypothesis 3, which says the Jacobian cannot be 0, which means that the Jacobian does not change sign, okay? It doesn't go from, in the entire region, the Jacobian doesn't switch from positive to negative or something. It either stays positive or stays negative. Then in that case, being that the area is positive, then we have to pick and choose, basically. So out of this formula, we end up slapping the absolute value on the Jacobian. That's just to make sure that our result come out to be positive. Then that is all. And then yeah, so but generally speaking, the area is the double integral of the Jacobian over the new UV plane, as long the UV universe, as long as we pick the right sign. Okay, so then and also I should mention that when the Jacobian is bigger than 0, then the clockwise description of xy, the gamma xy, will correspond to the clockwise description of gamma uv. And if Jacobian is less than 0, then the other way is true. That is just the result of observing the plus and minus sign in here. And yeah, if you spend some time thinking about it, you can probably figure out why that is the case. Now, in the previous example here, notice that the clockwise description of gamma xy is not the same, okay? Because this one goes one clockwise or something, and the other one goes counterclockwise or something like that. I can't remember which way it goes, but the point is they go differently. But if the Jacobian is positive, then they will go the same way. At least I think that is what this means. Well, anyway, it's just a matter of, the question is just a matter of the answer is positive or negative. So I don't want to wear myself out thinking too much about that. So let's go to the next page. So let's make a subdivision triangle of our xy. And then, so we have a bunch of subdivisions, okay? And each one has area delta sk. And then we're going to slap this thing through the transformation onto the UV plane. So there's a bunch of little triangles all corresponding where it's as triangle SK prime. So we have the subdivision. The original little thing is, well, it just, you can imagine that we'll subdivide this thing. And the little thing here, originally is called delta SK. Maybe I should draw it bigger. And then transform over here, okay, some other object, and it will be delta sk prime. And this transformation is one-to-one. So each subdivision here can be perfectly transformed into a bunch of subdivisions on this side that completely covers it with no repeats. So everything works because the transformation is one-to-one. Now then in that case, we will have then the area of delta, the original area of course, will be by the formula that we just figured out, okay? Each area will be equals to the integrating in the new region with a Jacobian slapped in there. So that this just comes from what we just proved for area only. Now, if this is in this case, then this integral, we're going to slap on the MVT by pulling it out, okay? Pulling out the middle part, okay? There's a point in there that this works, and that equals to, pull out the stuff inside, and equals to this thing times the area of the triangle S, because we're integrating over this part. So then, so this the mean value theorem, always very handy, okay? And then we have, and this is true for a specific point in here, okay? And then, but we are going to then assign the original point that corresponds to the new point. The new point is UKVK, where the Jacobian the formula works. So we'll find its original point, which we'll call it XKYK, which corresponds to this UKVK. And then we are going to calculate the area, okay? Now, the original formula for calculating we're not calculating area, we're just calculating the whole thing. Now, we'll put F in there, this calculation. Now, by definition of in Theorem 1, Chapter 6, that just says that this integral exists. That's it. So, this integral then is the limit of the subdivisions, the diameter, the subdivision going to 0, and the sum of f times the delta sk. And then we'll slap the delta sk formula we just figured out, that is that thing in here. And that will be, and then slap xk, which is g of ukvk, put it all in here. So we got this thing right here. So this is, again, by Theorem 1, that is, by definition, is the integral that we're looking for. That is on the previous page. That is, that thing is exactly the definition of this thing right here. There is the double integral f, g, and h, and then Jacobian d, s, u, v. And now look at that again. Then you can see why that would be the case. Okay, that's exactly the double integral. And now, in writing this down, we have to pay attention to certain things. That is, this limit exists and approaches the right place. But what about the norm? That is, what about the delta? Delta one side, the delta approaches 0. Does that necessarily mean that the other subdivision approaches 0? It does, and it does because of uniform continuity, and because of G and H are uniformly continuous. Then when the domain is restricted, so does the range. Okay, that's the definition of uniform continuity. And we'll just take it as that. Okay, uniform continuity was mentioned in page 172, and but basically uniform continuity just means that everything is in order. Okay, if the domain is restricted, the range will also be correspondingly restricted. That is, it become as small as necessary. All right, so that concludes the proof of this theorem. Okay, and then and we should mention certain things. That is, that in the result of this thing, when we look back at the theorem, okay, let's go back to the previous page and look at the theorem. The hypothesis 2, that is the second requirement, says that G and H has to be in C2, right? And that's necessary because at one point we had to calculate C2. We had to do H12 and then the H21 right here, which is why they have to be. Let's see, yeah. Anyway, we needed the second derivative at one point, so we have to require them as part of the hypothesis. However, you notice that the result, they don't actually show up in the result, which suggests that perhaps they're not really necessary. Okay, so somehow we can get away without requiring them. That the C2 maybe can be replaced by C1. However, we're not going to go into that because the proof becomes more complicated. So we'll just stick with the C2, and then we'll go for that for now. And also another bit about the other requirement is something about, yeah, and requirement 4 on the theorem on the previous page says that Rx and UV has to be both regular, simply connected regions. Well, okay, but we can, again, if that is not, the simply connected business is not necessary because we can just cut up the region into chunks such that they are connected. Simply connected if they weren't before, okay? And then make each part the same. And being that we're doing integration can be added together or broken into chunks, and it all adds up nicely. So we don't have to worry about it. However, we will state theorem 9 as is and not reduce the requirements just because, well, most of the time it works, okay? So that is that. So next, let's look at example A. Now, example A is a quick, simple example. So please do that yourself, as I have done here. That besides what the book says, you just have to, well, try out the theorem 9 by plugging in stuff, okay? We have, so I have example A right here. You just, plug in the U and V and calculate what the Jacobian is, that sort of thing. Yeah, and then everything, and then do the integration. Or the way I did it is just plug it into some calculator. And I wasn't going to do this by hand. I'm too tired for that. So here's I'm plugged it in. Okay, the different integrations, and they both calculating both ways of theorem 9, and you notice that they do come out to be the same, and as the book says as well. So please do that yourself, and we'll go on to the next page. Next, let's go to page 243 and look at section 5.3 subsection. Let's consider a surface that's given parametrically and with two variables where x is g uv, y is h uv, and z is k uv. Then we have in that case, we have three Jacobians. Okay, now pay careful attention that the Jacobians has to be in that order. Okay, where J1 is Jacobian of HK and J2 is KG. Okay, it goes from K back to G, and J3 is GH. All against UV, and then the D is the square root of the sum of those three things. Now what that is now what is all the stuff? Okay, now sigma then corresponds to the region RUV of the UV plane. That is we have right. So we had, this is being that is parametrically given. Okay, now suppose G is, so then sigma has a certain range of where U and V can move. So, but anyway, let's move on. Suppose D is not 0. D is the square root of sum of the squares. So D is not 0 in RUV. So then at least, so then J1, J2, and J3 can all be 0 at the same time. So let's say that J3 is not 0, okay, in the entire UV region. Then we're going to calculate gamma, which is the acute angle because between the normal to sigma and the z-axis. And if we calculate that, we'll figure out that secant gamma equals a d over J3. Now, how do we know that? Here is how we did this. Originally on page, this is back in chapter 3, okay, on page 106 and 107, we have a formula for gamma that is in the same form. That is, if we have some parametric surface and that is parametrized by u and v, then theta, which is the normal vector is xu cross xv. And that will be now and then normalized, of course. That will be the normal, okay, as the graph shown here. This is on page 106. I should hold on to this page better. No, wrong page. This one. Yeah. Okay. So anyway, please look at theorem 6 on page 106 carefully, and with that, please calculate where the book got this. That is, what is that is the theta, which is xu cross xv divided by the normal, is equal to j1 over d, j2 over d, j3 of d. I'm talking about the vector here, okay? It's identical to this. If we define j1 is this Jacobian, j2 is the Jacobian, and so on. Well, this is identical. That is and x1, and in the translation of here, what happens is then we have x1 will be correspond to the x, okay, will be called x in our current page, and x2 will be y, and x3 will be z. And then when you do the calculations, you will realize that it all works out as I have done here. So please do this yourself to make sure that the whole purpose of this is to confirm that secant gamma is indeed d over j3. So here's how I calculate it. See, because xu, we'll call it, being the zeta is xu cross xv as given on page 106, right? So I did the cross product here, and then and xu, we'll call it g1 h1 k1, and then xv will be g2 h2 k2, and then d will, and then when you do the cross product, you notice that that's exactly what it is. That each part of the cross product is exactly the j1, j2, and j3, and specifically the cosine gamma, which would be theta dot k, right? Because then that will be the angle, and which is, when you calculate this thing, the cosine gamma is exactly j3 over d, where d is the sum of the square roots. And so secant gamma is flipping this thing around, which is d over j3, and that's how you calculate all this stuff. So please do this yourself, okay? It shouldn't take that long. I mean, you know, you do one cross product just to confirm that, because this was not done in the book directly. So please do that, so that is clear to you where did this come from. But anyway, and I wrote down the results here as well, and yeah, so that is that can be considered as a definition of an alternative definition of theta. That theta is this pile of stuff. Of course, on the other page, there are various ways of representing theta, the normal, okay, that which we did before, but right now we don't care about that much, so we'll just go with this. So that is that. Now so after all that busy work, then you eventually will figure out that be convinced that that secant gamma is indeed d over j3. Okay, and then we can, and now that we know that, we can move on. Now, if our xy is the projection of sigma on the xy plane, then we have, by theorem 7, which is on page 233, this particular formula, this formula right here. We have, so the integral of pxyz is the integral of this thing being projected on the xy plane of all this stuff, and this part being the secant gamma, and that's direct following theorem 7. Now let's look at theorem 7 to refresh our memories. See theorem 7 here, and you can see right here. Okay, theorem 7 says the double integral of sigma of some function is the same as that function projected on the xy plane of the same function. With secant gamma here. This thing here is secant gamma. It says so right down here. Okay, the radical in the equation b is equal to secant gamma. We mentioned this earlier. So the entire radical is secant gamma. So and following the theorem 7, let's confirm back to where we are right now. We have so that's how we got this. See, the integral of the surface is the integral of the projection on the ground of the function times secant gamma, and then dsxy. All right, so far so good. So then next, we are going to apply this theorem 9 that we just did, which says that, so we are now at this point, okay, that is, we're integrating over our xy, right? Now, theorem 9 that we just proved is integrating over our xy. And what does it say? The theorem xy says that if you integrate over our xy, you can transform it into our uv, and this is just the previous page, 241. Okay, and then you put f in there in terms of uv, and then you slap the Jacobian in there, okay? And then you'll be dsuv. So that's what we're gonna do. We're gonna take this whole thing right here, take this whole thing, okay, and replace xy with u and v's, and then slap the Jacobian in here. What is the Jacobian? The Jacobian is the partial gh partial uv, as we have seen in the previous page, right? See, the Jacobian is the partial gh and partial uv, so that's what we're gonna put in here. So add the Jacobian. So we're gonna slap the partial gh and in here, and that will do it. But what is partial gh partial uv? That is exactly J3. Okay, we call it J3 in this story. So if we put J3 in here, and then so the dsxy equal to J3 times dsuv. So then if you put the J3 in here, then that J3 cancels out with the J3 on the bottom, and then we got we just have this thing left, and that is very nice. All right, right. So the J3 is, of course, in this formula is also under absolute value, so everything works out. See, this is under absolute value, so the other one is as well. And yeah, so the absolute value J3 cancels out, and what do we have? We end up with this neat little thing with J3 disappeared. But although we are stuck with D, and D might not be a happy thought either, because D has a square root in it. But still, we got to this point, so that's pretty good. Now, so that is done assuming that J3 does not vanish. Now, if it's the other two J's that's vanishing, then we just project it to a different plane, okay? That is the z-axis, the y-axis, the new z-axis, or we can look at it on the side or something like that. Anyway, so everything will work out exactly the same. And also, if not one of the Jacobians is different from 0 throughout R, that sentence means that each Jacobian might be 0 at different points, but they cannot be consistently 0, okay? I mean, because then the whole thing will collapse and we got nothing to say. So they might be 0 at different points. And none of them like completely non-zero throughout the region. If that is the case, we can still divide it into chunks, okay? Until where the Jacobian is non-zero throughout the little chunk, and then get this to come out anyway. Because we're doing integration, and integration can do addition very easily. So we'll just add it off, and everything will still work out. Therefore, the equation 8, which is very important, and when we'll be needing it in the homework, that is equation 8 then works out in all cases. And notice that, look at equation 8 more carefully. Then you notice that equation 8 does not care that who is the main axis. That is, it doesn't, the surface sigma does not need to be cut just once parallel to some axis. We don't really care, okay? The equation 8 works for all kinds of good stuff. And because everything is symmetrical, and we don't really consider which one is the main axis that everything else is represented with. We just, you just put the whole lump in, and it'll work out. So pay careful attention to equation 8, and keep it in mind when you do homework, especially do this kind of transformation. But equation 8, the only hard part is the d, okay? It has, take the square root, and that probably won't be very comfortable. But anyway, square root of sum of squares, the whole thing might be a giant headache. But still, it looks good on paper, okay? We just have the transformation neatly, just plug in the new variables and slap in the d, and then we're good to go, theoretically. So then with that said, let's look at example B, okay? We're finding area of the sphere. We're finding the area of the sphere again, right? With the transformation already given to you, okay? The spherical coordinate transformation. And you need to, the book says, as you can see, simple computation gives d equals a squared sine phi. Now, is it really a simple computation? I suppose it was simple enough, but it wasn't short though. I mean, I had to do all this stuff and try not to mess up, but I eventually did get to the right answer, okay? And so please do this yourself, Okay, calculate J1, J2, J3, and D squared, and eventually get to D. And once you get to D, then everything comes out very, very nicely. See, the integration is very simple. So D is the hard part. But in this case, D turns out to be a nice, clean little formula, which you can plug in. And I was able to do the integration without even using a calculator because it becomes so simple. And this is actually simple. Okay, this is not as simple. This is tedious, but please do that yourself. Okay, and that would be the end of this page. I will finish this section in the next video.